So here's an example truss we're going to take a look at. And so you can see on the diagram here that we have a pin support, we have a roller support, we have a triangle, just a basic truss here, and 85. I'm not going to put units on it, but you could call it 85 pounds, you could call it 85 newtons, kilograms, it doesn't matter what it is. And the same thing with the distances, we're not going to put a unit on that just for this demonstration's sake, but we've got a total of 6 units going in this direction, and we have 4 units going in this direction here. So this truss is a little bit different. It's not on the ground like we saw in the previous truss, like it's not horizontal. This would be something that would be mounted to, say, like the side of a wall. So maybe this is like your chin-up bar in your gym for your physical fitness unit. So something like that, but it's still a truss. It's just mounted to the wall. So we're going to go through the method of joints, and we're going to solve for all the forces, both the internal forces and the external forces on this particular truss. So the first step in the method of joints is what I like to do is I like to start out by kind of redrawing this truss as a free body diagram. And so I'm going to put in here a couple things. Let's start by labeling this. We're going to call this joint A. We'll call this one joint B, and then we'll call this one joint C. We already know that there's 56.31 degrees for this angle right here. If we didn't have that information, we would need to solve for that. Just know that we could have done that by looking at the inverse tangent of the opposite side over the adjacent side here, so opposite over adjacent. So that would have looked like the inverse tangent of 6 over, what is that, 4, and that would have given you 56.31 degrees if we had to do that, but we don't have to do that on this particular example. So we're going to go ahead and we're going to create a free body diagram here, and I'm going to have to draw this fairly small because we need a lot of room to write everything else out. So those are our 3 joints that we're looking at, A, B, and C. And then I'm going to draw my internal members. I'm actually not even going to put any directions on this yet, but we're just going to draw these out in blue to represent our internal members. And again, this is just my strategy of doing this. I'm sure other people do it a little bit differently. The pin support, you can see, is right here. It has 2 reaction forces, one in X, so you can see I drew that one, and it has one in Y right here. And the roller support has 1, and in this case it's going to be an X. So we'll put that in right there. And we also have the 85 pounds that is going to go this way. We already know the direction on that. It's going to be 85. All right. So our forces in blue are going to be our internal forces. Forces in red are going to be our external forces. And we've got our free body diagram drawn out. We have all our information, and we're ready to move into the second part of this. The second part of this is we're going to solve for all of the red forces. So we have 3 reaction forces that need to be solved for. We need to know, given this 85-pound load at the 4 feet, what is each reaction force? What is each support having to hold? All right, so we're going to do that using a couple different equations. So the first equation we have is a moment is equal to a force times a perpendicular distance. All right, so we know that this 85 pounds creates a moment, right? It causes the truss to rotate about this point right here. Okay, and remember this truss acts as a unit, so the whole truss rotates, not just one member. Okay, and it rotates in this direction. So if you remember, we said that from the moments video that clockwise moments are going to be negative and counterclockwise moments are going to be positive. Okay, so the 85 here produces a negative moment, and that causes the truss to rotate this way, but something has to like push back. And so that would be the job of the roller. The roller is going to have to push back this way. Kind of, it's a bad drawing here. Hang on. right? So it's going to have to create a moment this way to oppose this guy here. All right, now I'm pretty sure that it's going to go this way, because if that one's going this way, that has to counter it. But since it is a unknown, we're going to just assume that it is going to be a positive moment. All right, so we're going to assume that this is positive, and if for some reason it's not, then our math will come out with a negative answer. And we already know that this one here is a negative moment. All right, and so what we're going to do is we're going to look at the sum of the moments and set them equal to 0, and that's going to give us our reaction force here. Now, so we've kind of ignored these two up here. We've looked at the roller support, but these two pin reactions, we can include those in our equation, but if a moment is a force times a perpendicular distance, and this is the point that we're going to rotate around, right? So the 85 causes a rotation around this point, then the distance from this reaction to the pin or to the joint is 0. So therefore that doesn't create a moment. And the same holds true with this guy here. The perpendicular distance, if it's pointing this way, then the perpendicular distance this way is also 0, and there would be no moment created there. So using the pin support as your rotation, as your point of rotation, will really kind of negate two of these and allow you to solve for this one. So it'll negate 2 variables out of 3, and then we'll solve for the roller each time. Okay, so let's write out the equation. Sum of the moments is equal to 0, so we've got the sum of the moments is equal to, and we'll take what is the moment created by the 85. Well, it would be the force times the perpendicular distance. So I have 85 times the distance, and in this case, it would be the distance to the perpendicular distance to A. So that would be 1, 2, 3, 4. So that would be 4. And we already said that that is going to be a negative moment. And then we're going to add that to the next moment, which would be the moment created by the roller. And since that one is going this way, the perpendicular distance would be 1, 2, 3, 4, 5, 6. Okay, so we would have 6 times, and then it would be the reaction force at C. Okay, and then we'll say that that is equal to 0. All right, and so when we do that, we find out that this is negative 340 plus 6 RC. All right, so that would take 340 to this side equals 6 RC. We divide that by 6, and then we would get the reaction force at C is equal to a positive 56.67. Okay, so this positive number that we got right here basically just says that it doesn't mean it's a positive moment or a negative moment or anything like that. I mean, it does come out positive moment, but it means that the assumption we made at the beginning, calling this a positive moment, was correct. If this number came out negative, then that means the assumption I made here was incorrect and it actually goes the other way. So we would have to change our arrow direction there. So this simply means that our assumption is correct. Okay, so we have a positive moment right there. So that's good. All right, so we're going to come over here and we are going to update our little free body diagram to say that this does in fact go that way, and this number is 56.67. All right. Once we have our roller solved for, and we know that this whole truss is in static equilibrium, meaning that it's not moving, rotating, it's not going anywhere, it's fixed, we can actually then, once we solve for the roller using the sum of the moments, we can use our static equilibrium equations, the sum of the forces in x equals 0 and the sum of the forces in y equals 0, to solve for our other two reaction forces here. This is just saying that all the forces in x have to balance out, and same thing with y. So in this case, I know that I have like this is not in x at all, this one is not in x at all, but this is an x, and this is an x. So since that's going positive x, I could say the sum of the forces in x equals a positive 56.67. And then I don't know what this one is, so I would have to assume positive again. Again, I'm always going to assume positive, and then if my assumption is incorrect, then I can fix that up here. So I'm going to take that out for right now, but we're just going to assume that the reaction force at A in the x direction is positive, so plus that equals 0. And so we would find out that the reaction force at A in the x direction is actually equal to negative 56.67. So that actually means that since it came out negative, my assumption was wrong. It's going to go that way, 56.67. Then we can do the same thing here with y. So I already know that that's an 85 going down. Basically, according to this equation right here, if I have 85 going down, I have to have 85 going up. The equation on that would look like the sum of the forces in y. We would have a reaction force at A in the y direction. I would assume it's positive. That's always my assumption. So positive y, and then minus the 85 equals 0. So that means the reaction force at A in the y direction is 85. So I was correct. We're going to say that's positive 85. Okay, so step 2 is complete. We have all of our red forces here, our external forces accounted for. Now we're going to move into each one of these joints. So we're going to isolate the joint and then use static equilibrium equations to solve for that particular joint. All right, so I'm going to take this joint right here, and I'm going to move it down, and we're going to redraw that. So I have the force that goes this way, I have the force that goes this way, and then we had this one here. All right, and so you've heard me say that we're going to assume positive on everything, but when we're looking at internal members, remember these are two force members, right? So they can either be in tension or, so I actually don't like drawing that in red. We'll just do, so if this is in tension, then we're going to represent that with the arrow pointing away from the joint, and we're going to call tension positive. Okay, it doesn't matter if it's going up or down or left or right, it doesn't matter. If the arrow is pointing away from it, we're going to call it tension, and that's what we're going to assume tension, meaning we're going to assume positive. Okay, and then the other option we have is compression, and compression would look like the arrow pointing to the joint, and we're going to say that that's negative. So the only time this is going to really come into play is like right now when I am redrawing this and having to make some assumptions here. So I'm going to assume that this is positive and this is positive, meaning they're both in tension. So I'm going to assume tension, and then let's write in what these are. So this is going to be the force of AB, and this one's going to be the force of CB. Okay, all right, and then I already know that this guy here is 85. Okay, and we know our angle is 56.31. So that goes right there. Okay, so now I'm not going to worry about the tension and compression anymore. Again, I only really worried about that as far as making my assumptions. If I come out with a positive answer, then that means that this member is in fact in tension. If I come out with a negative answer, then it means that my assumption was wrong and we need to change that arrow direction. So we're going to use the sum of the forces in x equals 0 and the sum of the forces in y equals 0. Alright, here we go. So let's start out if looking at x. So in this case, FAB has an x component and FCB is in x. So that's two unknowns. I'm not really going to be able to solve for that. But y, on the other hand, FCB does not have a y component, FAB does, and 85 does. So we're going to solve for y first. So the sum of the forces in y is equal to, now this one appears to be going up in y, so we're going to say that that one is positive in y. So to get the y component, we're going to take the sine of the angle, sine of 56.31, and multiply it by the force of AB. And then we have the 85, that's negative, so negative 85 equals 0. Okay, so what we end up with is, we end up with the force of AB, that should be AB, force of AB is equal to 85 over the sine of 56.31. Okay, and what that gives us is the force of AB equals 102.16. So this did come out positive. Okay, so because that came out positive, that means that we are in tension. So that's good. So we know that this guy here is 102.16. So I can come up here and fill that in, 102.16. We will put a little tension. Actually, let's do that in a capital T here. So that member is in tension, and that means that my arrows are going to point away from the joint on both sides. It can't be in tension over here and compression over here. It's the same bar. So all of it is in tension. Okay, now we're going to do the sum of the forces in X now that we know what this one is. Okay, so we'll do that. I'll try and do that right here. We'll say the sum of the forces in X equals, I have, looks like this guy is going negative X, and so is this. So I imagine we probably will come out negative here, but that's okay. So we want to pull the X component out of this guy. So we've got the cosine of the angle, 56.31, and we're going to multiply that by the hypotenuse, so that would be 102.16. But again, we said that that guy is going negative, and then force of CB is also going negative, so minus the force of CB equals 0. Okay, so what we find out is that if we add this to the other side, we find out that the negative force of CB is equal to what looks to be 56.67. So that actually means that the force of CB equals negative 56.67. So that tells me that this member is in compression. Okay, and that means that my arrow direction here was incorrect. So that's going to be a negative 56.67. So when we go up here, I'm going to actually change this arrow pointing that way and this way, and you'll see that it comes out 56.67. And we'll put a little compression sign underneath that. Okay, and then finally, so now we only have, we solved for these two members, we just have one member left. So we're going to be strategic about this, and I can choose joint A to solve, or I can choose joint C. A has like 4 members, C has 3, so there's fewer here, but also C has no angles, so that's great. So we're going to pull C out, and we're going to put it, I don't know where, but let's try it right here. Okay, so we'll put that there. We've got that going this way and this going this way. You'll notice that those numbers balance out already. Right, that's good. If I have 56.67 going right, I gotta have it going left. I'm gonna assume tension on this one, so pointing up, and X is already done. All I have is a Y component, so we'll do the sum of the forces in Y equals 0. And if I only have one force in Y, the sum of the forces in Y equals, this would be member AC. It's going to be the force of AC equals 0. So that member actually carries no load. So that is 0, and then as far as arrows goes, it's in neither tension or compression. So, so I've had kids ask me before that, well then why don't you just get rid of that member? It's not carrying any load. Well, it's what we would call a zero force member, and it is necessary. We can't get rid of it because then the truss would become unstable and it would no longer be statically determinate. But and it's only in 0 in this particular loading configuration. If you were to take this 85 pounds and move it to here, well then that would be carrying 85 pounds. So, you can't necessarily take it away, but at the same time, you might have some trusses every now and then that have members that aren't carrying any load in particular configurations. So there you have it. We have solved for our entire truss. That would be our answer right there. And then obviously we have all our work to show. Let me know if you have any questions, and good luck.